the world is.
Rebecca doing this problem.
Hi! So for part A, we are asked to write out a few terms and a general term for the function given. So whenever I see that, the first thing that comes to mind is using the fab4. So in other words, we're just going to manipulate the function that is given to us to resemble a function we already know with the general term we already know. And in this case, it is 1 over 1 minus x. So you can see here what we're doing is pulling out that 2x, making that x squared a negative x squared and subtracting it so that we have that form from the fab4 of 1 over 1 minus x. And now that we've manipulated our original function, we can plug it in for a general term, which in this case is x to the n. So when we add our own function in there that we've manipulated before, our general term becomes 2x times negative x squared to the n. And part of the reason that manipulating this function was so easy is because we know our center is about x equals 0, so that made our lives easier. We didn't have to worry too much about manipulating the x as much. Now, once we have this general term written out, all we have to do is plug in the various n values starting with 0 until we get the desired number of terms, which in this case is 4. So just by plugging in n equals 0, 1, etc., we are going to get our first 4 terms and our general term from before. Okay, so in part B, we're trying to find out if the series at x equals 1, it converges to f of 1. So the first thing that I want to know is at x equals 1, does our general term that we have written out before even converge? And the answer is yes. Just by looking at it, we can tell that by the alternating series test, pretty much by the definition itself, we know that series we created in part A will in fact converge. Now the real question is, well, what's it going to converge to? And this is super simple. All you have to do is look at the beautiful little series we already have written out for ourselves and plug in 1. And we're going to have 2 minus 2 plus 2 minus 2, and it looks like it's going to keep going on and on. So it appears to be converging at 0. So now let's compare it to when we plug x equals 1 into our original function. So f of 1, you're going to see in just a moment, actually comes out to 1. So the answer is no. They do not converge to the same value. One converges to 0, the other converges to 1. And in terms of why that happens, we're going to explore why a difference occurs a little bit more in part D. So stay tuned. Okay, so given that the derivative of the natural log of 1 plus x squared is our original function f of x, we can alternatively conclude that the antiderivative of our original function is the natural log of 1 plus x squared. So with this knowledge, in order to write the first 4 terms of our new function, the natural log one, which I'm just going to call g of x, all we have to do is take the antiderivative of each of the existing terms. So as you can see, that's exactly what I'm doing, just writing out all of our terms that we found in part A, but now just putting them in integrals with the dx. All we have to do from there is integrate one term at a time until we get a new series of terms. And those series of terms are going to be the first 4 terms for this new function g of x about x equals 0. And we're just finishing up that integration right here. Pretty basic. You don't even need u substitution, just using our powers. And that's it. So part D is asking us to find the value of A that makes the statement the absolute value of A minus the natural log of 5/4 less than 1 over 100. So as soon as I saw the natural log of 5 over 4, I wanted to compare it to the natural log of 1 plus x squared, which is our new function that I'm going to call g of x. So I set 5 over 4 equal to 1 plus x squared and solved for x to get 1/2. So just like we did in part B where we looked at the series using x equals 1, we're going to do the same exact thing here, looking at our new series with our x value being set to 1/2. So here I'm just writing that out, plugging in 1/2 whenever I saw x in our series from part C, and then right below I start doing the math, did it kind of fast here, and wrote out the actual values. So as I'm writing them out, I know there's something interesting when I get to the third term, which is 1 over 192. Well, we know that 1 over 192 is less than 1 over 100. And this is starting to make me think of max error problems that we have done, which revolves around the remainder theorem. So basically, once we see that the third term is 1 over 192, we know that by the remainder theorem, the difference between the sum of those first two terms at x equals 1/2 and g, the new function of 1/2, we know that that difference is less than 1 over 100, which means that A, as stated previously, is going to be the sum of those first two terms. So 1 over 4 minus 1 over 32 gives us 7 over 32, which is our value for A.